Hi everyone, welcome back. So in this video, we're going to talk about one of the most powerful concepts in computing, which is referred to as the memory hierarchy. The memory hierarchy. What we're going to see is multiple different types of memory, multiple different ways of storing information, and we're going to look at some of the patterns that take place with these different types of storage. Frankly, there's engineering trade-offs for different types of storage, and how we manipulate those trade-offs for an optimal scenario. Okay, so we'll get into that. Let's look at some different types of storage first, and let's look at some of the metrics that we can kind of calculate or determine related to these different types of storage. So let's start with a hard drive. Right, here's a hard disk drive. These are kind of a lot of people have solid state drives now. But this kind of creates a good illustration is to look at a hard disk drive where you actually have a spinning disk, right? You actually have a spinning disk with mechanical components, right? Where you have some actuation and you have this head that'll actually move depending on what area, what memory regions need to be accessed. Okay, because of the mechanical nature of a hard disk drive. All right, in relation to computing terms, it's actually quite slow, right? Quite slow. Might seem fast in terms of everyday human experience, but when we talk about the speed of processors, it's actually quite slow. So, give an example. We look at this, we could say, okay, right, we're talking about something around maybe 15 milliseconds of access time, right? People can argue about how we want to about what the number should be. They change all the time. There's some caveats to it, but I'm trying to just look at the big picture. We don't want to get lost in little details here. We're just trying to look at the general big picture in terms of access times, and we don't want to get stuck in terms of nitty-gritty details. Okay. Well, if you made an assumption of 15 milliseconds here, you're talking under 1,000 read writes per second. Okay. But you can have quite a bit of storage, right? It's not uncommon to have a terabyte of storage or more nowadays, right? And these numbers are changing all the time, okay? It's also non-volatile, which means that the data persists whether or not you have power or not, right? Very important to have some sort of non-volatile storage because, frankly, you want to be able to shut your computer off or have the battery die on you and not lose all of your files and everything that you've been ever created. You don't want to have to run everything that needs to have power 100% of the time for the entire duration of, say, your life or the computer's life. All right, so we have this hard disk drive, and we're going to come back to these numbers momentarily. Okay. You also have your main memory, your dynamic random access memory, your DRAM. Okay, and again, you can argue on some of the numbers here. They're changing all the time. I don't really care about the specific numbers. I'm looking at the general trend, and we're going to compare these in terms of the general trends here. And the big trend here is that if we look at DRAM access time, right, you're talking about something, under 70 nanoseconds or so for being able for access time. So you're talking compared to for hard drives where you might have been talking in around 1,000, we had 667 was the example there. You're talking about millions, okay? Maybe 14 million, 15 million read writes per second, right? And, a lot of people have 8 gigabytes of storage or so, right? And again, all these numbers change. It is volatile storage, which means if you lose power, the data's gone, okay? All right, so we've got some of these numbers, and I'm just, again, don't get too bogged down in the specific numbers. The key thing is we want to look at a general trend in comparison between the speed comparisons between the DRAM and a hard disk, right? And if the kind of numbers that we used as examples here, which are realistic, if we look at them in terms of speed, we're going to see that there's your disk I/O is about 200,000 times slower than your memory I/O. Okay, so you're talking much slower. Okay, so that's the general thing. Rather than getting bogged down in this exact number, how much slower, the key idea is it's a lot slower. It's much slower, right? And if you're using a solid state drive, right, you're going to have a much faster. Your solid state drive is going to be a lot faster than a disk, but still, the trend holds true where your DRAM is going to be a lot faster than your solid state drive. Okay. Storage, we have the flip scenario going on, right? DRAM is expensive compared to your hard drive, right? Solid state drive is a lot more expensive than a hard disk, okay? But it's also faster. So there's a trade-off between basically speed and cost, right? If we want to form a storage that's really fast, you're going to pay for it, right? And so we have this balancing where we can have a lot of storage for a given amount of money, or we're going to have a smaller amount of storage that's really fast. And computers are built where we have all of them, right? We have faster storage that we have a small amount of it, and we have slower storage where we have an awful large amount of it, okay? So in this example, we have the 125 times difference, right? Right, in terms of disk I/O, or your disk, I shouldn't say I/O, your disk is about, it's just called 100 times larger, okay? We have different levels of memory. We're going to look at these as a hierarchy. At the beginning of the video, I said we're going to refer to something as a memory hierarchy, and we're going to show this information as a hierarchy where we have some sort of levels. But before we do that, let's look at a third different type of storage. And this is something you really get an appreciation for by doing some assembly language programming, that you have your register file, right? You have your registers, your CPU registers, okay? These are, here's an example when we look at like D flip-flops, right? When we look at register file, there's something that they're made out of the same type of material as the CPU. So if you're looking at, say, transistors here being used for the different gates, right? These can be exceptionally fast, right? They're operating at the speed that the CPU is needing them to, right? At the speed of the CPU itself, right? And we can have access times that are under a nanosecond, so under a billionth of a second, right? We'll look at more specific times later on in the class, right? But the general trend is true here as well. Is here we have exceptionally fast access times, but we have a tiny, tiny little bit of capacity, right? If we had 32 registers and each register was 4 bytes, we got 128 bytes of capacity. So that's puny. A tiny little amount of exceptionally fast, but also extremely expensive CPU registers, okay? So if we put these on a table, okay, we start seeing something along the lines of this, right? Where we can even draw something to kind of get a sense of this, where if we wanted to say the size of something down here, right? If we looked at, say, your hard drive, right? The hard drive has a lot of storage. So if this is your hard drive, and this is the amount of storage, okay, it's quite large. It's quite large. Okay. If we look at the speed here from being fast to slow, right? I drew the hard drive at the bottom because it's slow in comparison. So if we go up, this is where we start seeing a hierarchy form, okay? And we say we look at your main memory or your DRAM, okay? It has a smaller amount of storage, okay? So the amount of storage is smaller, but it's further up. It's faster here, right? Smaller storage, but faster. So here's our speed, okay? And then up here, if we have our registers, okay, they're exceptionally fast, but we have the smallest amount of storage, okay? We can also plot cost here. If we plot cost per byte, okay, where the amount of money it costs per byte of the registers is extremely expensive versus very inexpensive for the hard drive, okay? So this pyramid shape here is typically how the memory hierarchy is drawn, right? I give examples of 3 levels. In reality, you have many levels, okay? But rather than getting bogged down in specific numbers, I don't really care. What I care about is when we look at the overall trend between these different levels, okay? The overall trend indicating that the speed, right? There's a significant speed difference when we go from one level to another, as well as significant cost difference. Okay, faster memory costs more, and because of that, we use less, right? So we have a small amount of very expensive memory, and we have a large amount of inexpensive memory, right? Now the key is to maximize trade-offs. That is the number one key when it comes to the memory hierarchy. Maximize trade-offs, right? So if we're running a program, right? If you've got a program that needs access to data, which they all do, right? The goal here is that the program is accessing the CPU registers, and that data that it needs is propagating up the memory hierarchy and preventing the program from having to wait significant periods of time. So what we want to do is we want to maximize, right? All our programs can only operate on reading and writing directly from the CPU without having to slow down. And this is a larger topic than we will get into today, but effectively what we want to have happen is to maximize the data we need being up here, right? So we want the data that we need, we want it to be up top in the hierarchy. In old data that we just want to preserve or we might need a little bit further down the road, we want that further down. So we want the data we need up here. So the data we need soon or very soon. And then further down the hierarchy, it's data is not needed for some time. All right. So it's a prioritization that's going on. Okay. Right. This way we can still preserve data that we're not using for a long time. We still have it. We're preserving it. Right. But the data that we're going to be accessing that we really want to be reading and writing from, we want that up here at the top. Okay. We'll go deeper into that. I'm just going to show a couple images that are frankly showing the same kind of general trend. Right. We get faster as we move up the hierarchy. We've got cost also moves up, and size goes down as we go up the hierarchy, right? So we want to design systems to maximize speed, yet minimize cost. Okay, right? So we want to be maximizing how much we're using the really, really fast memory in terms of our, right? Where things that we just want to store and we don't need for a while, we can kind of push deeper and deeper down into the hierarchy. Okay. All right. The general numbers are going to, depending on where you look and but different architectures and everything, they change. Right. Here's one, looking at Intel's example, right. And they're not showing the hard drive, but the general trends is you're talking about, things getting faster as you move up, right. Bigger as you move down, right. As well as costs being more significant at the further up the hierarchy. Okay, so let's stop the video there. And what we're going to follow up on in subsequent videos is we're going to look at the from the processor's perspective. We're going to actually look at the assembly language for how we have instructions that use memory. Okay, and we're going to look at that in relation to registers. Okay, but that will be something that's a topic in of itself, and we'll save that for the next video.